So, hi everyone, I am Pankaj Kumar from IIT Kanpur. Today I will discuss about the longitudinal control strategy for automated vehicle at signalized intersection. So, first let us give you the outline of this presentation. First, I will begin with the introduction, then we will discuss about the reinforcement learning, and then we will discuss about the model training, and after that we will discuss about the result and some result and discussion. And in the finally, we conclude my presentation by summarizing the main takeaway. So let us start with the introduction. Vehicle control at signalized intersection is particularly challenging due to inherent complexity of the decision-making process, which involves the interaction with the traffic signal, surrounding vehicle, and safety constraint. So in this presentation, our main objective is to longitudinal control of ego vehicle at signalized intersection by adjusting acceleration, deceleration. So the intersection consists of a two scenario. When the leader vehicle is present, that time follow the leader vehicles, and the second scenario, whenever the leader vehicle far away, that time we need to follow the traffic rules like traffic signal and speed by balancing safety, efficiency, and comfort. In all these scenarios, the human driving is often suboptimal in this case, which motivate to develop in such an intelligent control strategy to achieve better safety, efficiency, and comfort. So, achieving this objective, RL provide the better control framework by enabling the vehicle to learn the optimal strategy through the interaction with the environment. So RL basic, so let us first give you the basic of RL. The basic of RL consists of the five key element for agent, state, action, reward. So this is the basic five element. So now we move to the how the RL is working. So in this case, the RL agent take a state as a state as an input and take an action, and based on the internal dynamics of the environment, a state get updated to the next state, and based on the next state and the current state and the action that they have taken, the environment also calculate the reward function, which give the feedback to the RL agent. So this is the basic this is the basic framework of the RL agent. So now we move to the we move to the different component like a state. So a state first defined as the whatever the factor that influence the agent action that's come into the state. So a states there are in this case the state is the ego vehicle speed, relative speed, a space, and distance to a stop line, and the traffic signals that's come into the states. And in this case the action is longitudinal acceleration and deceleration. Now we move to the reward function. So reward function that guide the learning, that guide to the agent, that guide to agent learning through feedback. So in this case, whenever this is a very critical component while solving this type of problem. So in this case, we have defined reward function based on these five parameters like safety, efficiency, comfort, traffic signal, and a speed limit. So let's discuss one by one. So first, reward function that we have space headway, which I have modeled based on the log normal distribution. So in this case, our main objective is to whenever the leader follower vehicle keeping the space headway equal to the desired space headway, that time it will get the maximum reward, otherwise it will get the minimum reward. So in this way we have modeled the reward function for efficiency. Now we move to the second reward, which is related to the traffic signals. So in traffic signals, the whenever the amber light is there and the red light is there, in that time it take two decision, either we need to stop or we need to go. In this case, what we have did, we have calculated the action, which is the difference between the DTL minus stopping side distance. If the action is negative, that time vehicle do not have the enough space to stop before the stop line. In this case, if the ego vehicle decelerating, that time it will get penalty. And when X is positive, that time vehicle have enough, the ego vehicle have enough space to stop before the stop line. In that case, if the vehicle is accelerating, that time it will get penalty. And whenever the signal is red, that time what we have did, we have placed a virtual vehicle with zero length and the zero speed at the stop line, and based on that they will get the reward functions. So in this way we have formulated the reward function for the traffic light. Now we move to the third reward function, which is related to the comfort, and the comfort which is defined based on the jerk value, jerk value which is defined as the change in acceleration with respect to time, and based on this equation we have provided the reward function for the jerks. So now we move to the the third reward function, which is related to the safety, and the safety parameter that we have defined based on the time to collision. That means how much time that we have left to collide with the leader vehicle whenever the leader vehicle and forward vehicle traveling with the same speed. So in this case, whenever the TTC value lies between 0 to some threshold, that time it will get reward based on these equations. So and also the speed limit, when the speed limit is when the speed of ego vehicle is greater than the predefined speed limit, that time it will get penalty. And also one reward, that is whenever the collision is happening, that time it will get maximum penalty minus 50 that we have taken. So once we have defined all the reward, and then the final reward is something like this. So this is the weighted average of all the reward that we have previously defined. If the space is greater than 0, if the space is less than 0, that time the collision reward that the agent will get. So once we have defined the reward function, now we move to the model training. In this case, we have taken 3 types of model like DDPG, TD3 and soft critic. And once we have selected the model, then we have trained this model based on the real world data set and simulated data set. The real world data set that's come from the NUMA data set and the simulated data set. So the training results something look like this. This y-axis represents the normalized rolling reward and the x-axis represents the episode. And all the 3 models, the rolling reward looking like this. Once we have trained the model, now we need to test this model. So for the testing, we have testing based on 3 different scenario. First scenario based on the overall trajectory performance, then the response to the leader vehicles, and then the traffic signal compliance. So let's move the first one, overall trajectory performance. In this case, we have taken 3 matrices. First is the safety matrices, which is based on the TTC. Second one is the efficiency. Third one is the comfort, which is related to the jerk. So as we can see, our all RL model keeping larger TTC value, that means safer sides, and the keeping lower space headway and the higher comfort. That means the overall we can say the RL model keeping lower space headway without compromising the safety. So now we move to the second test scenario, which is related to the how the RL model behaving when to the leader vehicles. So in this case, the blue one. So blue one this represents the real one, this one DDPG, and this is the SAC. As we can see, this the real one keeping the larger space headway, as we can see in the our RL model keeping lower space headway without collision with the leader vehicles. So in this case, now we move to the third test scenario, which is related to the traffic signals. So in this case, what we have placed, this is the leader vehicle and this is the follower RL vehicles. So in this case, we have placed the leader vehicle beyond the signal and the RL vehicle before the signals. So as we can see, whenever the signal is red, our RL model stop before the stop line. That means it do not violating the traffic signals. And when this signal turn from red to green, the RL vehicle start moving, as we can see particularly in this equation. This signal turn to green, then the vehicle start moving. So in this case, the vehicle is clearly maneuvering the traffic. So now we move to the conclusion part. So in this case, we have formulated the reward function for multiple driving objectives, such as including traffic signals, compliance, asymmetric acceleration, deceleration, safety, efficiency, comfort, and maintaining the desired speed. So, and the second thing, model validated with the compliance with the traffic signal, stability of acceleration and deceleration, safety in response effective to enhance traffic flow and ensure comfortable driving experience. And also RL-based vehicle control system efficiently maintain safe following distance, responsible to the traffic signals, provide a smooth acceleration and deceleration. If you are interested in to this particular work, you can follow these papers. Thank you. This is the references, and thank you.